Welcome. In this section, we're going to look at rational expressions and a couple of applications of them with indirect or inverse variation. And we're also going to look at the domain and how that might be restricted with certain functions. So first of all, let's just start off looking at the definition. What does it mean to have a rational expression? Well, we can, in general, just say that a rational expression is an expression that contains a variable in the denominator of a fraction. So, when we talk about expressions, these are different than equations. They're just expressing a relationship. So this isn't necessarily an equation, though we can have rational functions and equations as well. But when we talk about expressions, we're just talking about a relationship that's being expressed. And one way to remember, this term rational, it's kind of a weird, why do we call a fraction rational? It's the name that we give to any numbers we say that can be expressed as a fraction. So it's just a classification of a whole number set of any number that, if it could be expressed as a fraction, which includes whole numbers, because, for example, 3 over 1, is a expression of 3. So 3, the whole number 3, can be expressed as a fraction. So 3 falls into the rational category as well as 1/3. Okay. So in general, we call them rational expressions just because there's a whole set of numbers that are called rational. So, and here I have a bunch of examples of a rational expression. You can see they involve fractions, and in each one of these, there's a variable, specifically a variable in the denominator. If I just had x over 1, we wouldn't really say that's a rational expression because the variable isn't in the denominator portion of the fraction. Also, one of the things that we have to watch for with rational expressions, because in a fraction setting, it doesn't mean anything, or it actually is illogical to divide any number by 0. For example, 3 divided by 0 would say, hey, okay, we've got 3 items, and we want to break them into subgroups that have nothing in them. In other words, subgroups that are empty. And that's impossible. We can't take 3 items and break them into subgroups that have nothing in them. So we say that 3 divided by 0 is not 0, but is undefined. It's not possible for me to do that, so we say it's, with this symbol, undefined. Right? That's just in general numbers and operations. We can't divide by 0. Now, I do want to point out that a 0 divided by any number is equal to 0. This is allowed. Yay, we can do that. But we cannot have 0 in a denominator. So, with an expression, since expressions are ways for us to express a relationship, since we can never divide by 0, and fractions are a way of expressing division, we have to restrict our expressions, because generally, with any expression, we can plug whatever we want in for the variable, and we're going to get a result, right? But if we plug something in for x that results in a 0 in the denominator, that would be a bad thing. That's something we can't have. So any value that would result with 0 in the denominator is not allowed. So if we go up to these expressions up here, we see for these first two, they both just have x in the denominator, right? So for me to get 0 in the denominator, I would simply have to substitute x equal to 0, and I would end up with 1 over 0 here, which is not allowed. And here I would end up with 0 minus 7 over 0, which is negative 7 over 0, which again is not allowed. It's the empty set. And so we would say for these expressions, x cannot equal 0, because 0 results in a 0 in the denominator. All right, so that's for those particular functions. X cannot equal 0. Let's take a look at this one. What is the value that would result in 0 in the denominator? Well, we see that with x minus 7. If we don't want that expression to come out equal to 0, we can actually set this equal to 0 and solve for x, and that will tell us what x cannot be. So x cannot be 0 plus 7, 7. This is not allowed for that particular expression because it results in 0 in the denominator. For this one here, we have a trinomial here, so I'm going to take it and set it equal to 0 and find out what I would have to have x equal to in order to get 0 in a denominator. So with this, I know I have a negative here, a minus 10, so I know that my signs have to be opposite, and I want two factors that multiply to give me 10 or negative 10 and add up to give me negative 3. Well, that would be negative 5 and 2. Negative 5 and 2 multiply to give me negative 10 and add up to give me negative 3x. So I can see there that x cannot equal negative 2 or positive 5. Both of those values plugged in would result in a 0 in the denominator. There's lots of different types of equations where we can end up with a rational equation, right? So we end up with a variable in a denominator. And in one of these is the distance formula. Now, we're going to start off looking at something that's maybe a little more familiar, which is just the straight-up, typical way we express the distance formula. That distance is equal to the rate that I'm traveling at multiplied by the time that I am performing or driving or whatever, traveling at that speed, at that rate. So D equal RT is what we call the distance formula. And this is what we would call a phenomena, or which is represented by the equation that has a direct variation. With direct variation, as my variable x increases, we see the y increase as well. Sorry, I started to do a decrease there. So with direct variation, they always go in the same direction. As x increases, y increases. So as the time or the rate that I'm traveling increases, the distance will increase as well. All right, now let's take a look at this in a very specific way where we just have two variables, right? So I'm going to look at d equal to 35t. My rate, in other words, is 35, and we're going to say 35 miles per hour. So we want to know what's the distance with 35 miles per hour multiplied by time. And what I want to do is just to take a quick look at the graph that we get with this. And so I'm going to take this over 1, 2, 3, 4. So I'm going to put time down here because we always put the independent variable, which is the variable over here, on the x side. And then distance will be here. Generally, whatever it's solved for, we put on the vertical axis. So let's mark that off as well. And I'm going to put for time 1, 2, 3, 4. This is going to be in hours. And then distance is going to be in miles. So we're going to say, just to make it easy, 35, 70, 105, 140, and then 175. Okay, so just to look at this, we know that this is a linear relationship, right? Because both variables are being raised to the first power. Nothing's in a denominator. This is not a rational expression or equation, more specifically. So I'm going to put d, actually we'll put t and then d here, and we can look at some points, some ordered pairs. So at 1 hour, we know 1 times t, or I'm sorry, 1 substituted into t times 35 would be just 35. So I know 1 and 35 goes right there. 2 would be 2 times 35, which is 70. So that gives me this right here. 3 gives me 105, and so on and so forth. You can see I kind of set this up to graph really nicely. And in fact, 0, 0 is also, if I haven't driven it off, time is equal to 0. I haven't gone anywhere. Now in this case, and which is true with a lot of real world problems, we actually would probably, this is not a big deal, but we'd probably actually not put an arrow here. We'd probably put a 0, or not a 0, but just a dot, because we can't go into negative time or negative distance. Right, so I'm going to just tweak that a little bit there. And put a dot. There we go. So this is a graph, and it's a line. It's a straight line, though my graph is a little bit curved there because of imperfections in my spacing of these points. But straight line, that's a type of graph that we would see with a relationship that has a direct variation where distance varies directly with time. Now, since we started out with the direct variation, d equals rt, any equation like this we can mess with. Like with d equal to rt, I could solve this for either r or t. If I solved it for r, that means I want to get r by itself, so I would get r by itself by dividing both sides by t, thus eliminating it on the left hand or the right hand side, and giving me r is equal to d over t. And we could do the same thing by isolating t by dividing both sides by r. So you can see I can also transform the same equation, but we're simply looking at it from a perspective of time or the perspective of rate. So I want to look at how this changes our graph. No longer do we have, if I look at, when we looked at distance in relation to time, distance and time had a direct correlation, a direct relationship. As the time that I'm traveling increased, the distance that I have traveled would increase as well. What we see with a inverse variation is that as x increases, y will actually decrease, right? So they have that kind of opposite effect. Now, it doesn't just give us a line, though, because you'll notice that when we have a t in the denominator, we have a restriction now. T, we know, time, cannot be equal to 0. All right, so I went ahead and took this one. So I set a consistent distance of 120. Let's just call that 120 miles. And so I put a number for that so that we're just looking at the relationship between r and t. Rate and time. So again, r is going to go over here. R is my rate that I'm traveling at. And time is going to be down here. And let's just go ahead and put a few things here. I'm going to say 1, 2, 3, 4, and I'm going to do by 30s here. So 30, 60, 90, 120. And let's start by graphing some points here. All right. Now, one of the things we know that time, sorry, I wrote this completely incorrectly over here. Time cannot equal 0. One thing you'll notice that in equations, whenever we have something that we cannot, t or a variable cannot be, that either A, we would have a hole at that point, a hollow dot at that point, or B, there's going to be a invisible line that our graph approaches but never quite reaches. And so we can kind of get an idea of what would happen in this case if I got close to 0. For example, let's look at 0.5. If I plug 0.5 into here. If you go 120 divided by 0.5, so we're putting 0.5 into, oh, I should put t here, and then r here rather than x and y. the rate R would be double what I have there. It would be 240. So 240 is going to be somewhere way up here. I'm just going to kind of guess where it would be as an approximation. So at 0.5, which is half the distance between 0 and 1, we would be way up at 240. Okay? And even if I go smaller than that, let's say 0.1, if we divide that by 0.1, we actually end up at 1200, which is, well, way off. I'm not even going to try to plot that. So what we see is that as we get closer and closer to 0, it's getting really high. Let's go ahead and go forward there, and we'll plug in 1. Well, 120 divided by 1 is just 120. So at 1, we're right here. At 2, we would be at 60. So right here, that's 120 divided by 2. At 3, 120 divided by 3 is 40. So just a little bit above 30 here. And then at 4, we're going to 30. And we can divide it by 5. We can continue, but I want to just sort of go ahead and draw this out. What we see is this graph that is following this trend, where in fact it'll never equal 0, because in order to get 0, we'd have to have a 0 on the top. If we have 0 as a result in a fractional setting, you have to have 0 divided by some number. That's the only way. So if we want 0, we have to have a 0 on the top and a constant on the bottom. That's the only way to get 0. So our graph is going to get closer and closer to the y value of 0, which is at the x-axis, but also it's never going to cross the y-axis either, because we can never plug 0 in. So we have this relationship here. This is the type of graph we see with a rational equation. Wherever our excluded value is, that's where we're going to have a line that we cannot cross. Okay, let's look at some more problems that involved inverse variation. And so we're going to look at a very simple one here. We're just told that suppose y varies inversely as x. So here we're being told the type of relationship that we have. This is the general equation we have for inverse variation, where y is equal to some value c. Whenever we see c, we think constant, which is the opposite of a variable. Even though c is a variable, it's representing what would be or what will be a actual number. So sometimes we'll use c there to just clue into the fact that we're going to expect to have a number there. But to adapt any situation to a particular relationship, we have to figure out what c is for each situation. Okay, and that's also true for direct variation over here. In fact, the steps going through this stuff is similar, though I'm not going to really deal with direct variation. If they said y varies directly as x, then we would be using this one. So y varies inversely as x, so I know I'm going to use that. I'm going to know y is equal to c over x. And then we're given a scenario. Now, the point of this scenario is to give us a value of x and y that defines the relationship so that we can create an equation that would work for every x and every y. So what we're told is, hey, here's one scenario. When x is equal to 6, y is equal to 3. So I can go, all right, well, let's plug that in. Y is 3 when x is 6. And so what we want to do with this is to use this to figure out what c is. Remember, c is kind of the one little mystery we need in order to cement this relationship that happens when y comes out to be 3 whenever x is 6. So I just need to solve this for c. And I do that by multiplying both sides by 6. Here we had c divided by 6, so I do the opposite. I multiply by 6, and that eliminates this. So I see that c has to be equal to 18. So now what I have is the actual equation for this scenario. Y is equal to 18 divided by x. Now in a lot of these problems, this is my rational expression, not expression, but in this case equation, because we have an equals there and more than one variable. But this is my inverse variation formula or equation for this situation. Then they usually give us another step to take. They say, okay, now that you've established that relationship where x is 6 and y comes out to be 3, if that's the case, find out what y would be if x was equal to 8. So we can substitute 8 in for x. And we see we get a fraction there. We see that y is equal to 9/4, so a fraction, when x is equal to 8. I actually want to just take a second here to go back and look at this relationship and have it make sense to us when we say that rate and time are indirect or inversely related to each other, meaning as one goes up, the other goes down. We talked about that. So think about time and rate in terms of travel. So this 0.5 is not just a 0.5. The 0.5 represents 1/2 of an hour. And then for this amount of time, if I'm going 120 miles, the question is, what is the rate that I need to be traveling? So if I want to, after half hour, be at 120 miles, what is the rate that I need to be going? And what we see is that if I want to travel 120 miles, I need to be going at 240 miles per hour. That's the rate I need to be traveling. If I want to reach 120 miles and I want to do it in 1/10 of an hour, which would be 6 minutes, I would need to be traveling at 1,200 miles per hour, because remember, R is our rate. If my time is 1 hour and I want to go 120 miles, then I need to be going at 120 miles per hour. So you can see as my time increases, the rate at which I need to be traveling decreases. If I give myself more time to travel 120 miles, I can do it at a slower rate of speed. But of course, I'll never be traveling at 0 miles per hour, right? I would never be. This would make this whole idea, if time is 0, if time is 0, I'm not going to make it 120 miles. And also, as time gets larger and larger and larger, all that means is I have to go at a slower and slower speed. There's never going to be a time where I'm going to be going at a rate of 0 and that I'm going to somehow reach 120 miles. Okay, so let's look at another inverse variation. Here we have, suppose in a dark room, light intensity is inversely proportional to the square of the distance. So light intensity is inversely proportional to the square of the distance. So again, we know that inversely, that's an inverse variation, so that means it's in the denominator. So I'm going to use the inverse variation formula here. We know that inverse variation in general, this is just general, is some c value over some x. But let's be more specific in this case. We're talking about light intensity, so I'm going to put L for light, is proportional, or is inversely proportional to the square of the distance, so I'm going to put D for distance. And it's not just distance, it's distance squared. It says the square of the distance. So as we move away, light becomes less and less and less. All right, again, we need to know what this C is. What is the constant we have here? And so they give us an example. And the point of this is for us to find C. At a distance of 2 meters, the intensity is 100 lux. That would be our light intensity. So again, that's kind of giving us our X and our Y. That's not kind of, it is giving us our X and Y. So we have 100 lux is equal to some C value over 2 meters. So 2 meters distance, but it's distance squared. So of course that becomes 4. So to solve this for C, we want to multiply both sides by 4. So we see 400 is equal to my C. So that gives me my equation now. L is equal to 400 divided by D squared. Then they have us do one more problem. They say, okay, well, what will light intensity be at 5 meters? Notice it's in the same type of measurement we have over here. I always want to make sure that we're talking about the same thing. If they said 5 feet, we'd have a problem. We wouldn't be able to do that because our example was given to us in meters. So we would have to go back and figure out what that would be in terms of feet. But regardless, they match this time. So, and that's my distance. So we're going to find light intensity, 400 divided by 5, my distance, 5 meters, squared. So that's 400 divided by 25. Which is 16. And the units that we had for light was lux. So we would have 16 lux. All right, let's look at another example here. Here we're talking about average cost. We say manufacturing a new t-shirt. The setup cost is $600 and the per item cost is $6. So maybe 600 is just the big old setup, so that never changes. But for each item that we make, it's going to cost us $6. So we're going to add to our cost. So I'm just going to put C. This is our cost equation. C is equal to 600 plus 6x. So if I made, for example, 10 t-shirts, the cost would be 600 plus 6 times 10, or 600 plus 60, which is $660. That would be the cost of my making of those 10 t-shirts. So that's a lot of money to make 10 t-shirts. I better make a lot more, right? I'm probably not going to be able to sell these 10 t-shirts for like $100 each. Maybe if they're really, really amazing t-shirts, but that probably would never happen. So that's just an example of the cost that we've been given. Now, what they say secondly is find the average cost per item if X items are made. I kind of covered over this here accidentally. So find the average cost per item if X items are made. So we want a new equation here, which is an average cost per item. And it's cost divided by item. Now, our item in this case, we used X to represent it. So the cost is given by this equation. So really we want to go the cost equation, 600 plus 6x, and then we want to divide that by the number of items. Well, the number of items is represented by X. So this would be my average cost equation. And that is a rational equation because there is an X in the denominator. Now, one thing I do want to point out is that we cannot cancel out this X here. This X and that X cannot cancel out. Why? Because there isn't an X over here. Now, you could rewrite this, though I wouldn't necessarily recommend it, but 600, we can take that X and put it under each part. So 600 over X plus 6X over X, where here, since all it is a times going on, a 6 times X division is the opposite of multiplication, and so, yeah, that's when this can cancel out. But the problem that we have doing it over here is that this is a sum, and a division does not undo a sum. And so we can't just cancel it because there's an x here. We would have to, it has to be a simple product. It needs to be written as a factor. We can only cancel out factors. So this could be written, though again, I wouldn't necessarily recommend it, but there's nothing wrong with doing it. 600 over x plus 6. That would be a equation that represents, or if you don't have the a equals, that would be an expression that represents the average cost per item. All right, one more example here. We're going to wrap this up. The number of women and men enrolled in a college can be modeled by this. So we have this linear equation that's modeling, and this one in particular is the number of men and women. And T, I believe, is going to represent years. Let's keep reading. So this would be women for time, and then we have men, depending on time. T is defined as years after 1980. The question is saying, find the percent of all enrollees who are women in year T. Percent of all enrollees. A percent is always a part of a whole. Just kind of, let's think about percent. Part over whole or total. So just in general, we could think of a portion over a whole. In this case, we want to think about men and women. So my total is really going to be all women plus all men. And what we want to find is the percent of who are women. So I want to have women on top. Now women were given as a function of time by 0.17t plus 5.59. And then on the bottom what I want is not just the men, but the men and women. So I'm going to have to take women plus 17t plus 5.59 and also add to that the men, which is 0.076t plus 5.38. Here I have my women added to the men. We should probably combine any terms that are like. Now on the top, there's nothing to combine. We have the variable term 0.17t plus 5.59. But on the bottom, I have a t expression here, t expression here. Since this is plus, I can pretty much just ignore the parentheses there. Now, if there was a minus there, I would need to distribute that minus into each term, into the parentheses. But we can go ahead and add those two terms together. So if I add those two together, 0.17t plus 0.076t, I get 0.246t. And then if I add the two constants together, 5.59 and 5.38, we get 7. 9 plus 8 is 17, and then 5 plus 3 plus 1, which would be 9, and then 5 plus 5 is 10. So let's go ahead and put this in green. 10.97. What I have here is an expression that represents the percent of all enrollees who are women in year T. So let's take this one more step. Let's find, since this is what this represents, let's find the percentage of women enrollees in the year 2000. Well, T is defined as years after 1980. And we do that a lot of times with time. We set a beginning year, so like T equal to 0, this would be the year 1980, right? And then T equal to 1 would be the year 1981. And the reason why we do this is to simplify the equations so that we're not dealing with really weird, big or really small numbers, and it just makes it easier to do things. Because also it's like t equal to 0 has a meaning. T equal to 0 means 1980, but what would the year 0 mean in reality, right? If we just said t was time, and we didn't define it as years since 1980, t equal to 0 would be like 0 AD or BC. I'm not sure where that falls, but like 2,000 years ago. And of course, we don't have data from back then, so it really takes on no meaning. So that's a lot of times with time we like to give it this starting point. So 2000, the year 2000 would be t equal to 20, because the year 2000 is 20 years since 1980. And so if I plug in 20 there, I have 0.17 parentheses plus 5.59, and down here we have 0.246 parentheses plus 10.97, and of course we're going to plug 20 in there, so I'm going to put 20 here, and we want to work this out. Now if you're going to put this into your calculator, you want to do both of these. If you're doing it all at once, put the top in parentheses. So hit the parentheses on your calculator and go 0.17 times 20 plus 5.59. Close those parentheses. Reason why is because the division here, the division bar represents division. So the fraction bar, represents division. And we want this sum to be divided by the bottom. And in fact, we want the bottom sum to go into the top sum. And additions and subtractions, if you remember in the order of operations, are always very last. They're the least important. And so we put them last. So the division would actually, this wouldn't work. It wouldn't add them and then divide the top into the top by the bottom if we don't have those parentheses there. The only things that would get divided are the last number you entered here, then the first number you entered there. Actually, the product would, it would just be that one. And so that's not what we want. All right, so once you have the top in parentheses and you hit divided by, then we'll put the bottom 0.246 times 20 plus 10.97. We get 0.5658 if we round it to the fourth digit, because what followed that was, there was actually a 7, but then that was followed by a 6, so that rounds up to 8. So this would be 56.58% of women being enrolled in college in the year 2000. And this would be an example of a rational expression. When we do averages, that's always a division. So if we're doing an average or a percent is a division. I think the previous one I misspoke there was our average example. But both of those involve division. And so in a rational, so if we're expressing them, we would need to express them as a rational expression.